The year 2020 was like no other. It all started when a viral pneumonia was detected in Wuhan, China, soon to spread and become a pandemic that caused so much distress and fear. The aim of this project is to propose a design for a primary school in Germany after studying the impacts of coronavirus, implementing the Passive House Building Code, simulating passive strategies to enhance the design, and comparing the results to achieve energy saving. In this presentation, we will have 5 stops. The first one will be the introduction. The impact of COVID-19 was drastic on schools. Several countries were assessing how to deal with the situation, and for many, options included remote learning. Moving on to the site analysis. From Dubai to Germany, to its capital Berlin, to an area in the southwest of Berlin called Dahlem. The site chosen is accessible by several roads and surrounded by many schools and universities. It is highlighted in light blue. Wind direction is from southwest and west. And this is the sun path. As for the temperatures, they reach a high of 23.7 in July and a minus 1.9 degrees in January. Next is the concept and design. The design was derived from the COVID-19 guidelines, the Passive House guidelines, and the immunity system concept. The COVID-19 guidelines for schools recommend one-way circulation, increased ventilation, several entry and exit points, open space, and having points for checking temperature. Passive House was put by Dr. Feist in 1999, and it relied on several things, for example, proper window insulation and proper orientation. As for the concept of the immunity system, it inspired breaking up the school into nodes and connecting it via a circulation path, just like the nodes and the circulation here. In Germany, there's an average of 20 students per class with ratio of 1 to 12 teacher to student. The school will operate at 40% and fit 80 students due to COVID-19. The Grundschule will comprise of 2 classroom buildings. On the ground floor, each will have a large open space that can accommodate a lab, an art room, and an eating space. On the upper floor, there will be 2 classrooms. The Grundschule will have 1 main building. Its ground floor includes the lobby, 2 clinics, and 2 isolation rooms. The upper floor is office space. In the ground floor, here is the main building with the 2 clinics and isolation rooms. Here is the classroom building's open space. These are the circulation corridors and the circulation cores. Students will enter through the lobby, where their temperature will be taken to move on to the assigned building and spend their day there to exit from there. For the first floor, there are the main building offices, and these are the classrooms. Desks were arranged to allow for 2-meter social distancing between them. Open balconies were integrated to allow for air circulation. Here's the final design. The fourth stop will be IES analysis. IES analysis will include first comparing the final design to the base case, second, comparing the base case to 3 passive strategies, and finally comparing the base case to adding all summer strategies together and all winter strategies together. Final design's building orientation was aligned with the site at north rotated 315 degrees. Optimum orientation with least energy is at building facing south at 0 north rotation. An annual profile was assigned to IES to include when the school is closed. Here is an example of assigning the annual profile. Moving on, materials were changed to comply with Passive House recommended U value. For wall, it was changed from 0.2 to below 0.1. For the roof, it was changed from 0.2 to below 0.1, and for glazing, triple glazing filled with Exonon was assigned for the passive house windows with a value of 0.8. Here's the base case design with 20% south-facing glazing, 4% for east, and 2% for west. To assign the scenarios for comparison, daily running mean temperature was used. The results were on days when the school was off. Thus, the next coldest and hottest mean temperatures were chosen, 10th of January and 6th of June. For the thermal analysis, there has been an overall reduction by different percentages throughout the day. Similarly, there has been a reduction in solar gain. The improvements also led to an overall increase in the temperature by different percentages throughout the day, while a significant solar gain increase was evident in the afternoon. The change between final design and base case resulted in decreases in cooling energy, room cooling load, and heating energy and room heating load. For the first strategy, the greatest sun altitude was obtained and used in triangle calculation to get louver length, where upper C case is the altitude angle, lower c is the window height, and lowercase a is the louver length. The prevalent cooler hues when louvers are attached represents reduced solar gain, which corresponds to reduced temperatures by different percentages throughout the day. A deeper look into the effect of the louvers in winter using insol reveals unwanted shading during the winter months. From there came the idea of folding the louvers in winter to reduce their effect. Having full louvers were compared to one-fold louvers and three-fold louvers. Folding the louvers 3 times resulted in temperatures closest to having no louvers in winter. Consequently, adding the louvers in summer reduced the cooling energy and room cooling load, and folding them maintained the required heating energy and room heating load. Three sun spaces were added to analyze their passive heating effect. A general look reveals increases in temperatures at 12:30 and 3:30 p.m. Let us have a closer look at the main building sun space. Temperature inside the sun space reaches almost 13 degrees Celsius during the afternoon. Adding the sun space resulted in increasing the temperature of the adjacent space starting from the afternoon when it stored enough heat. Let us have a closer look at the classroom building sun space. Its temperature reaches a high of 15 degrees Celsius in the afternoon, and that is when a significant increase in the adjacent space temperature is evident. In the summer, starting from mid-April, the sun space will be closed. Closing the sun space resulted in creating more shade represented by the cooler hues. The result is verified by reduced solar gain on June the 6th. Having the sun space closed in summer resulted in reducing the cooling energy and room cooling load. In addition, having the sun space in winter reduced the heating energy and room heating load. A high thermal mass wall with glass spaced at a cavity on its exterior, the trombe wall, was applied to several walls of the south-facing facade of the school. An overall look reveals that the trombe wall affected the temperatures positively in the afternoon, just like the sun spaces when they stored enough heat. It is interesting to note that the temperatures of the trombe walls themselves reaches 18 degrees Celsius at 2:30 p.m., just an hour before they raised the temperature of the adjacent spaces. The classroom has been more affected by the trombe wall due to a smaller area compared to the ground floor space. Adding the trombe wall reduced the heating energy and room heating load by 9% and 7%. Temperatures of the interior spaces that have trombe walls were recorded to see whether having vents will allow for cooler temperatures or not. Having no vents resulted in cooler interior temperatures. In summer, louvers will extend over trombe walls to shade them. For the summer passive strategies, the louvers will be extended, the sun spaces will be closed, and the trombe walls will be shaded. The more blue hues represent reduced solar gain. Consecutively, temperatures were reduced by different percentages throughout the day. Solar gain has also been reduced throughout the different timings due to increased shading. Let us have a closer look at the classroom. Looking at the right, that visible down push of wind near the window is due to having louvers. The concentrated yellow hue of 0.2 meter per second here is the recommended velocity for cooling by ASHRAE. As for the temperature, the mix of green and turquoise colors in the passive case on the right represents 9% decrease in temperature compared to the base case. The conditions in the passive classroom on the right are in closer proximity to the neutral zero. Finally, there has been an overall 33% reduction in cooling energy and room cooling load comparing the summer passive strategies case to the base case. For the winter scenario, louvers will be folded above windows and trombe walls, and sun spaces will be open. The pattern of afternoon increase when the passive heating strategies have collected enough heat is reflected here in the overall building temperature at 3:30 p.m. Solar gain has been increased too due to increased stored solar energy of trombe walls and sun spaces. Notice that the maximum solar gain occurred at 1:30 p.m. and that resulted in increasing the temperature for the coming 2 hours. Let us have a closer look at the classroom again. Notice that the interior temperature reflected the same pattern of afternoon increase and here by almost 50%. The green and yellow hues in the classroom of the passive strategies on the right corresponds to values of predictive mean vote that are in closer proximity to the neutral zero. Let us have a closer look at the space behind the sun space in the classroom building. Notice how there is a significant jump in temperature in the afternoon when the sun space has stored enough heat. Looking at the velocity between 3 to 4 p.m. in the passive case on the right, there are more green and light blue velocity vectors which represent higher wind speeds that are within the comfortable range of 0.15 for heating by ASHRAE. Here on the right, we notice more light blue corresponding to more air movement compared to the base case. More interior air circulation is recommended for COVID-19. The heating energy and room heating load were reduced by 10% for the cumulative passive heating strategies. To the final stop, the conclusion. For the passive cooling strategy of adding louvers, it is a simple strategy when calculated right, results in significant reduction in money and energy. For passive heating sun spaces, solar heat is collected, then transferred to adjacent spaces. The design of the school allowed for having two, and in the one in the classroom building worked better than the other due to several reasons. One, having it lifted above ground, which resulted in more solar exposure. Two, having the space behind it smaller resulted in more pronounced effects of sun space. And three, the flat elevation behind it reduced shadows that decreased solar gain. As for the trombe walls, they were assigned to the resulting south-facing walls after calculating the passive house 20% south-facing glazing. Reason was to maximize views and daylighting and to prioritize the more efficient window direct solar gain. The effect of the trombe wall was quantifiable in the classroom due to the classroom's smaller area. Improvement from final to base case was significant and was due to material and orientation change. Improvement from base case to strategies was most significant when reducing solar gain through louvers. For future research, sun spaces propose interesting thermal and aesthetic potential.